Welcome, class. Today, we're going to dive into a really sophisticated and frankly powerful calculus technique known as logarithmic differentiation. Now, I know that might sound a little theoretical, but I really want you to understand right from the start that this is a critical tool for anyone heading into business analysis, economics, or financial planning. This is the mathematical key, really, to modeling and understanding those dynamic systems where the rates of change are themselves changing, and let's be honest, that's a constant reality in the world of business. We're going to explore not just how to do this, but more importantly, why. Why is this thing indispensable for making smart strategic business decisions? All right, let's jump in.
So let's kick things off by looking at a very specific and pretty challenging scenario. As you see here, we're dealing with a function where another function is sitting up there in the exponent. Now, let's translate this into a financial model to make it real. Imagine your company has an investment portfolio where the principal, that g of x, isn't fixed. Maybe it's a fund where you're constantly injecting new capital, or maybe you're withdrawing it over time, so the base of your investment is always in flux. Now let's make it even more complicated. The interest rate, our h of x, is also not constant. It's a variable rate that's tied to market performance. This isn't your simple everyday APR, it's a dynamic variable. So the big question we have to answer is, at any given moment, what is the instantaneous rate of growth of this investment? That's the derivative, right? But how in the world do we find it? Our standard tools, they just fall short here. Let's think about why that is.
And this is really the heart of the issue we're facing. Think back to the power rule. Y'all know this one. The derivative of x to the n is n times x to the n minus 1. But that rule is built on the idea that the exponent n is a constant. It just can't handle a variable exponent. Okay, so what about the exponential rule? The derivative of a to the x is a to the x times the natural log of a. Well, that rule requires the base a to be a constant. In our investment scenario, as you can see, neither of them are constant. A very common mistake students make right here is to try and mash these rules together, creating some kind of hybrid, which just gives a completely wrong result. In a business context, imagine you were modeling your projected revenue based on a price elasticity model with this structure. A flawed derivative would lead to totally incorrect predictions about how price changes affect demand. I mean, that could lead to catastrophic pricing decisions. So clearly we need a better, more sophisticated method. Let's dig a little deeper into one of these applications, say economic production functions. Think about the Cobb-Douglas production function. It's a real cornerstone of microeconomics. In a modified version of that, your company's output might be modeled as a function of capital raised to a power that represents the elasticity of that output. But what if that elasticity isn't constant? What if it changes as your company scales up and adopts new technologies? All of a sudden, you've got a variable in the exponent. Now, if you want to determine the marginal product of capital, which is an absolutely critical metric for deciding on future investment, you have to be able to differentiate this complex function. This isn't just some academic exercise. This is fundamental to how you strategically allocate your resources.
So how do we tackle this beast? Well, a solution is a technique called logarithmic differentiation. And I want you to think of this not as just another rule to memorize, but as a really elegant multi-step strategy. The whole strategy is built on one of the most powerful properties of logarithms, their amazing ability to turn exponentiation into simple multiplication. We are going to use logarithms to literally transform the problem into a shape that our existing differentiation rules can handle with no problem at all.
So here's the formal definition. Let's break this down carefully. The key move here is taking the natural logarithm, or ln, of the function. Now, why the natural log, specifically? Because its derivative is beautifully simple. The derivative of ln of x is just 1 over x, and that little property is going to prove incredibly useful later on. I really want you to pay attention to the sequence here. We are not differentiating anything yet. First, we're just applying an algebraic transformation to simplify the whole expression. This prep step is the entire foundation of the method.
All right, very good. Now let's really dissect the mechanics of this whole process. We're going to walk through this in a logical, step-by-step way, so you don't just understand the procedure, but you get the mathematical justification for every single step. That way, you'll be able to apply this principle to any function of this type that you come across in the future. This slide really gets to the core of the strategy. Notice the emphasis on the word before. You see, the brilliance of this whole method isn't some new, complicated differentiation formula. No, it's in an algebraic pre-processing step. We're essentially taking our complex function, g of x to the h of x, and we're simplifying its structure by applying the natural log. What comes out the other side is a fundamentally different and way simpler expression. And this whole transformation is possible because of a key property you learned back in algebra, the power rule for logarithms, which, as you'll remember, says that the log of a to the power of b is just b times the log of a. Let's trace this process, one step at a time. Step 1 is just our given function. F of x equals g of x to the h of x. In step 2, we perform a totally valid algebraic operation. We take the natural logarithm of both sides of the equation. That gives us ln of f of x on the left and the natural log of the entire expression on the right. Now, really focus on step 3. This is the pivotal moment. This is the magic. We apply that power rule for logarithms to the right side. The exponent, h of x, gets to come down from its perch and becomes a coefficient, multiplying the logarithm of the base. Just look at that result. ln of f of x equals h of x times ln of g of x. The variable is no longer in the exponent. We have successfully turned an exponential problem into a multiplication problem.
And this slide really confirms what we've just accomplished. That complex, tricky exponential form has been successfully converted into a simple product of two separate functions, the function h of x and the function ln of g of x. We are now on familiar ground. Differentiating a product of two functions, that's a standard procedure, and we have a specific tool for it, the product rule. The problem is now completely manageable.
Okay, now we get to apply the calculus. We're going to differentiate both sides with respect to x. Let's look at the last side first. ddx of ln of f of x. This requires the chain rule. The derivative of the outer function, the natural log, is 1 over its argument, so we get 1 over f of x. Then we have to multiply by the derivative of the inner function, which is f prime of x. So that gives us f prime of x divided by f of x. Simple enough? Now for the right side. The derivative of h of x times ln of g of x. Here we just apply the product rule. It's the first function, h of x, times the derivative of the second, plus the second function, ln of g of x, times the derivative of the first, h prime of x. Once we have that entire expression, our final algebraic step is just to get f prime of x by itself, which we do by multiplying both sides of the whole equation by the original function f of x.
So, we've now mastered the mechanics of this technique. But the most critical question for any student of business or economics is always going to be, what's the practical use for this? Why is this relevant once I leave the classroom? And the answer is that the very type of complexity this method is designed to solve is absolutely everywhere in real-world economic and financial models.
Let's really consider one of these applications in detail. Imagine you are modeling the adoption rate of a new technology product. In the early stages, the growth is exponential, right? It's taking off. But as the market starts to get saturated, the rate of growth itself begins to slow down. That changing rate, that's your variable exponent. The base might be the current number of users you have. If you want to project future revenue and figure out the perfect time to invest in a next-generation product, you absolutely must be able to calculate the instantaneous change in your user base at any point along that classic S-curve. And logarithmic differentiation is precisely the tool that lets you analyze that kind of dynamic growth model.
This slide really wraps up the fundamental takeaway for us. A static model, well, that represents a world of constants. Think of an investment with a fixed principal and a simple, unchanging interest rate. It's a useful approximation, but it's not reality, is it? The dynamic model is the world you are going to be operating in, a world of fluctuating asset values, variable interest rates, and shifting market demand. Logarithmic differentiation is the key that unlocks your ability to go from that simplistic, static analysis to a complex, realistic, dynamic analysis. And that is the foundation of modern financial forecasting, quantitative risk assessment, and high-level strategic planning.
So I'll leave you with a final thought, one that really extends beyond calculus. The fundamental principle we use today wasn't about attacking a difficult problem head-on with a bigger hammer. It was about first transforming it into an easier one. This is an incredibly powerful paradigm for all kinds of business problem solving. When you're faced with a complex supply chain logistics issue, could you reframe the problem by changing your distribution model? When you're tackling a tough marketing challenge, could you transform your perspective by focusing on a different customer segment? The real lesson of logarithmic differentiation is that sometimes the most elegant solution isn't in finding a more powerful tool, but in changing the problem itself. That concludes our lecture.